Our next property of relations is equivalence. This is probably one of the most important properties of relations that you will come across. A relation R is said to be an equivalence relation if it is simultaneously reflexive, symmetric, and transitive. It's very simple. You need to check if it's reflexive, you need to check if it's symmetric, you need to check if it's transitive. If all three properties are satisfied, then it's an equivalence relation, otherwise it's not. A property of equivalence relation is that it partitions set A into what are known as equivalence classes of A. In other words, the way to think about this is I start with the element A and I want to find the equivalence class of A. And the way I'm going to do that is I'm going to look at what A is related to, and that will be the equivalence relation of A. So if A is related to B, A is related to C, A is related to D, then the equivalence relation would be A, B, C, D. Now, let's figure out what are some of the properties that are going to be here. So it's reflexive, and that means A must be related to itself, must be. Then if A is related to B, then B must be related back to A because the relation is supposed to be symmetric. Plus, it's transitive. So if A is related to B, B is related to C, then A is also going to be related to C. And because it's also symmetric, C is also going to be related to A. So in an equivalence relation, if I look at the set of what A is related to, then that is going to form this equivalence class of A. And now if I wanted to look at, say, B, and I wanted to look at the equivalence class of B, then equivalence of class of B will contain A because the relation is symmetric. It will contain C for the same reason. So essentially, if A is related to B, then equivalence class of A and B would be basically same. And that's what makes the equivalence relation interesting in mathematics. So let's look at some examples and see whether uh, these relations are reflexive, symmetric, transitive, equivalence relations, etc. So here we have xy, where x plus y is equal to 0. So essentially it includes 2 comma minus 2, 3 comma minus 3, minus 3 comma 3, etc. So these are a few of the relations. Uh, I want you to look at each one of these, and then I have the solutions on a few slides afterwards. So let's look at xy, where x plus y is equal to 0. So let's see, is this reflexive? Well, the answer is that it's not, because 1, 1 is not in this relation. It's not irreflexive either, because there is one pair which is in the relation. If x plus y is equal to 0, then y plus x is also going to be equal to 0. That means the relation is symmetric. It's not antisymmetric, because you can have 1 minus 1 and minus 1 1. Both are in the relation, but 1 is not same as minus 1. It's not transitive because it's possible that x plus y is equal to 0, y plus z is equal to 0, but x plus z is not equal to 0. For the next few slides, I am not going to sort of go through each property separately, but I want you to verify that each of these properties is in fact the way it is. That is, whether the relation is reflexive, symmetric, or transitive. or irreflexive or antisymmetric is what you expect. Okay, this is for when we have the relation x, y, and we want x minus y to be a rational number. So one observation that we can make about this is this relation is reflexive, it is symmetric, it is transitive, and that means it is an equivalence relation. So if I wanted to find out the equivalence relation of a number, say if I wanted to find the equivalence relation of say 1, then essentially that's going to require me to find all numbers such that 1 comma y is in the pair, and that means 1 minus y is needed to be a rational number, and that means all rational numbers will satisfy this property, and that means if I look at the equivalence class of 1, that is going to be all rational numbers. If I look at the equivalence class of, let's say, square root of 2, then it's going to be of the form square root of 2 plus x, where x is any rational number. The reason for that is if I choose any number in this set, the difference will be a rational number by design. If I choose anything else, the difference will not be a rational number. See if you agree with the choices on this slide. Or this slide. One more example. One more example. We can keep doing this for many examples. The reason I'm putting these examples on the slides is so you can check your intuition about each of these properties to make sure that it matches with the actual definition of these properties. So here is a summary of some of these. Uh, so for each one, we have identified whether the relation is reflexive, irreflexive, symmetric, antisymmetric, transitive, or equivalence relation. And these two relations are equivalence relations because they are reflexive, symmetric, and antisymmetric. Reflexive, symmetric, and transitive. And that's what we needed for equivalence relation. Once again, we have reached the check before you go ahead slide. I want to make sure you have understood the definition of reflexive, irreflexive, symmetric, antisymmetric, and transitive relations. In particular, I want to make sure you have realized that reflexive and irreflexive are not opposites of each other. Reflexive says that the pair AA is there in the relation at all times. Irreflexive says that it is never there. So there is a possibility that some of the pairs are there, but some are not. That will make a relation neither reflexive nor irreflexive. Likewise, Symmetric and antisymmetric are not opposites of each other. Symmetric says that if you have the pair AB, then you must have the pair BA. Antisymmetric says that the only kind of such reversible pairs you can have are the AA kind of pairs, basically where the two elements are the same. So they are not opposites of each other. In fact, a relation can be simultaneously symmetric and antisymmetric. It could also be neither symmetric nor antisymmetric. Once again, we have reached the end of the module, so go ahead and do the review quiz.